Hello everybody, welcome to today's video. We're going to be exploring exponential and logarithmic equations today. So the next couple videos are kind of culminating videos on what we've been learning these past few weeks about exponential and log equations, or just log functions in general. And we're starting to wrap up the college algebra portion of the class now and starting to move into trig. So these last couple of lectures will be some culminating videos. So today we're going to be looking at exponential and log equations. So we'll use the one-to-one property of exponential and logarithmic functions to be able to solve some problems here. We'll also solve log equations using the log properties that we looked at in a previous video. We'll use logarithms to solve some exponential equations, and then we'll solve some exponential equations that are written in quadratic form. Kind of this, they're kind of trickier problems that we see in the homework, so I wanted to address those as well. All right, so the first thing we'll look at here is the one-to-one property of exponential and logarithmic functions. And what that says here is our normal conditions, b needs to be positive and it can't be equal to 1. Then for any algebraic expression m and n, so we could just view those as maybe being numbers, but they could just be expressions like x plus 2 or x squared minus 5, or literally any algebraic expression you can think of, you can put in there, and the following will be true. And hopefully this is an intuitive idea as well, and it's true because we have one-to-one functions here. But what this is saying is that we have b to the m equals b to the n. We're saying both things are exactly the same. That is what equality means. And they have the exact same base. They both have base b. But one has an exponent of m and one has an exponent of n. Those are the only things that look different, but if everything else is the same, then m must be equal to n. So that relation of equality there is really giving us a lot of information about m and n, because if everything else is the same, meaning the bases are the same, then the exponents just have to be the same, because exponentials are one-to-one functions. And we get the same thing for logarithms if we have log base b of m being equal to log base b of n. So again, those bases need to match. Then we also get that m is equal to n. So we can use this property to help us solve some questions here. So the first one, we have 2 to the x minus 1. That whole thing is in the exponent there. And we have 2 raised to the 2x minus 4 with that whole expression in the exponent there. Since those bases are exactly the same, that means that we can just focus on the exponents. We can focus on just the x minus 1 being equal to just the 2x minus 4. Since those bases are exactly the same, and we have two expressions being equal to each other, the only part that doesn't match are the exponents, which means that those exponents must be the same. So now we can solve for x here. We can subtract x from both sides. We can add 4 to both sides. What do we get here? That cancels. This gives us 3. And this gives us just x on this side. So we get x equals 3. And we could always go plug this back in and make sure that this actually works. So this says that 2 to the 3 minus 1 should be equal to 2 to the 2x minus, 2 times 3 minus 4. And I think that's true. That says 2 squared is equal to 2 to the 6 minus 4, which is 2. So yeah, we get a true statement there. We checked our work, and we can be sure that that is the case. And this next one here, we have the natural log of x squared is equal to the natural log of 2x plus 3. Since those are the same base, the natural log, remember, natural log of x means log base e of x. It's just a different notation that one takes on. This is saying that the natural log of x squared is equal to the natural log of 2x plus 3. Well, that means that x squared must be equal to 2x plus 3. And now we have something that we can try and solve for here. If we get everything on one side, maybe let me scoot this over a little bit, because we're going to want to check our answers here as well. We're going to get x squared minus 2x. So if I subtract 2x from both sides, and I subtract 3 from both sides, then I'll get x squared minus 2x minus 3 equals 0. And this should factor. And we'll get x minus 3x plus 1 as that factorization, which tells us that x equals 3 or x equals negative 1. Now these are just proposed solutions. We need to go plug them in and make sure that they actually work. We can sometimes get extraneous solutions when we're doing these log equations. So remember that the domain of a log equation is just positive numbers. So 0 won't work, and any negative numbers won't work if we try and plug them into the log function. So we just need to go make sure that both of our proposed solutions here actually work. So let's check x equals 3. Well, if I put that in, I'm going to get the natural log of 3 squared being equal to the natural log of 6 plus 3. So yeah, we get a true statement, but also we're not in any danger of plugging in any negative numbers here. So this one totally works. If we want to check x equals -1, now you might be thinking, oh, it's negative, so we can't plug that in. But we aren't just plugging in -1 to the log function, we're plugging it into some expression, which is being plugged into the log function. And so if I look at the natural log of -1 squared, then that's equal to the natural log of 1, which is totally valid. We can take the log of 1. And then looking at the other side, the natural log of 2 times -1 plus 3, well, that's still the natural log of 1. So getting kind of squashed in the corner there, but we get the same answer. Either way, we never ended up plugging in the negative into the log function here, so we can be sure that both of these are actually solutions. So when you're checking your answer, remember that it's not that one of the solutions is negative, it's that when you plug it back into the log function, if you get a negative, that's being a result after plugging it in, that's when we need to throw that out as an extraneous solution. Here they both work though. So here is some reminder of the log properties that we looked at a previous video, and then also the definition here as well, because we can use these and put these all together to solve some of these other types of log equations here. So here we have log, and it has an unspecified base, which means that this is going to be log base 10. This is the common log. We just don't write it if we don't need to see it there. So what we're going to do here in our first step, looking at these first couple of terms, they're being added together. They have the same base 10. So we can use this first property here, the product property, and rewrite this as log. And I can turn each argument here into the product of a single argument. So this will give me x times x minus 3 as all the argument of a single logarithm, and this is still equal to 1 at the end. Maybe I can do a little bit more cleanup here, and I'll get log of x squared minus 3x equals 1. So like I had said before, this is log base 10. So at this point, we should use the definition, and we can actually put this back in exponential form, and I think that should help us solve this problem from here. So putting this in exponential form, this says that the base is 10, and when I raise that to the first power, I should get the inside of the argument here, x squared minus 3x. So that is putting that back in exponential form, and now we have something that we can totally solve. If I subtract 10 from both sides, then we'll get x squared minus 3x minus 10 equals 0. Now I think that this should factor, and we'll get x minus 5, x plus 2. If I multiply that out, that gives me minus 3 in the middle and minus 10 at the end. Yeah, so this tells me that x equals 5 or x equals -2. Now we need to go plug these back into the original equation and make sure that we don't accidentally plug in a negative number here. So looking at 5, if we plug in 5 here, yeah, no problem. We can take the log of 5 all day. And if I plug in 5 here, well, that gives us 5 minus 3, which is 2. No problem there. So plugging in 5 totally works. So we'll give 5 a box because that is going to be a solution. Let's check the other value here, which is -2. And I think we run into a problem straight away. If I try and plug in -2, we have log of -2, which -2 is not in the domain, so we can throw this out. This is an extraneous solution. All right, moving on here, we'll look at another example. So these are the same properties from the previous page, just a different question here. So we're asked to solve for x just like before. And what we want to do here, I think, is a good first step is multiply both sides by this denominator here so we can clear it out. So if I multiply the left-hand side by log of x, and I multiply the right-hand side by log of x, and again, this is log base 10. Here we get those logs to cancel, and we've got log of 5x minus 6 equals 2 log of x. So at this point, we might be tempted to use that one-to-one property of logarithms, but the issue right now is that this 2 is still a coefficient in front of this first log. In order to use that property, we need it to just be log of something equals to log with the same base of something. And then we can set those somethings equal to each other. So we can just use the power property in reverse and stick that coefficient in the power over there. So I guess we're using this property here. And we get that log of 5x minus 6 is equal to log of x squared. Now that we have just logs with no coefficient, or I guess a coefficient of 1 in front here, now we can use that property that says that 5x minus 6 is equal to x squared. And now this should go very similar to some other problems that we've seen here. If I get everything on one side, x squared minus 5x plus 6 equals 0. Then we can factor this left side and we'll get x, and this should be -2 and -3. Those will add to give me the -5 and multiply to give me +6. Yeah, that feels good. So from there we can solve for x. We'll get x equals 2 or x equals 3. And then we just want to make sure that all of those solutions actually work. So if I just kind of visually plug them in here, I can plug in 2 all day to just log, and that is fine. Same thing with 3. 3 also works here, so no danger there. And then in the numerator, yeah, I can plug in 2 or I can plug in 3. Either one of them will work there. I won't get a negative number. So there we go. Both of these work once we just kind of visually plug them in, again, just to make sure that we're not accidentally plugging in a negative value to one of those log functions. All right, in this next page here, we're going to solve some general exponential equations. So we saw on one of the previous slides that when the bases are the same, we can just equate those exponents. But here, there's no real way to turn 50 into 10 to some power. I mean, I guess there is, but the way you do that is with logarithms, which is what we're going to do right now anyway. So what we are allowed to do is take the log of both sides, and that's a valid thing to do because of the one-to-one property. So that's what we're going to do, and we're allowed to use any base that we want when we take the log of both sides here. So since we have a 10 as the base on the x on this side, I think it might be appropriate to just take the log base 10 of both sides. So again, if I'm not indicating the base here, we assume that it's 10. We'll take the log base 10 of both sides. Well, here, this just turns into x. We have the composition of inverse functions. We have the 10 to the x exponential function being plugged into the log base 10 function here. So this just results in just being x. They are undoing each other. We just get x back. And then on the right-hand side, we just have log 50. So we could have chosen a different choice of a base for our log there, and we'll see that in the next example here. But choosing a convenient form, especially when it's 10 or e, can be nice, and then you don't have to rely on doing a little bit of extra algebra. In this next example here, again, it would be nice if we could turn 5 and 7 into the same base, but there's just no way to easily do that. So what we can do is just take the log of both sides. So I'm going to choose the natural log because that is a button that I have on my calculator, and I can easily press that. That's why I'm choosing it. We could be using log base 10, but just for completion here, I'm just choosing different logs that I can easily put into a calculator. So if I take the log of the left side, I better take the log of the right side. Whoops. Natural log of 7 squared. Now I can use the property that says I can take the exponent here and kind of visually put it in front, but we're turning this exponentiation into multiplication. So we'll get x times the natural log of 5 is equal to the natural log of 7 squared. Now we can divide both sides by the natural log of 5. They cancel on the left, and we get that x is equal to the natural log of 7 squared over the natural log of 5. And we put that into a calculator. I have it written somewhere here. This is about 2.41 ... I guess I have log 50 here as well. This is about 1.6 699, blah, blah, blah. So another takeaway here is that we're choosing logs that we can actually put into a calculator and compute. We could, take the log base 7 of both, well, I mean, I guess that one makes a little bit of sense. We could take the log base 2 of both sides here, and that is a true statement, but I think it's not that helpful. We could solve for x still, but then we'd have to put log base 2 into some calculator, and that's not an easy thing to do with calculators that we normally have for these sorts of classes. So true, but not helpful, which is a comment I sometimes make. So there we go. There's some ways to solve some general exponential equations here when we can't easily turn those bases into each other. All right, looking at another example here. We're asked to solve for x, and this at first glance doesn't look like the easiest problem in the world, but I think that we'll see that this is totally doable. If we take a look here, this actually does appear to be in quadratic form. If we take a look, the exponent on this first term is double this exponent here, and then we just have a constant term hanging out. Right now it's on the other side of the equal sign, but we can deal with that. So we might notice that I could rewrite this as e to the x squared minus e to the x minus 56 equals 0. And now you might be a little bit more convinced that this does look like quadratic form. And I can use this substitution. We'll let u be equal to e to the x. And then I can rewrite what we have above here as just u being squared minus u minus 56 equals 0. And hopefully you agree that this seems like a much easier problem to solve. And so let's go ahead and do that. We can just factor this left-hand side. I believe that this factors, we'll have u and u, and then I think we'll have -8 and +7. Those multiply together to give me -56, and they add to give me -1. Yeah, I feel good about that. So then solving for 0, we'll get u equals 8, or u equals -7. So we've solved for u, but that's not what we were asked. We were asked to solve for x. We made this substitution of u equals e to the x, and now we should substitute back. So now using this substitution here that we originally made, we'll say that, u equals 8 or u equals -7, just kind of moving things up. It says e to the x equals 8, or e to the x equals -7. And now we have two solutions to solve. But if we look at this first one here, we will notice that there is no solution to this, because there is no variable that we could, or there is no number we could put on e to get a negative number. The graph of e to the x looks like this. Its range is always positive. There's no way that we'd ever get -7 down here. It just never hits that graph. So we can throw this out as an extraneous solution that happened to pop up as we were working through this here. But we'll take a look at the other side here, and that's where I think we will find an actual solution. At this point, we can take the natural log of both sides. Oops, I forgot to take the natural log of that side. Natural log of 8. And then on the left-hand side, these are undoing each other. We are plugging the exponential base e function into the log base e function, so we just get x back, and that is being equal to ln of 8. So there we go. We have solved for x. Maybe I could write that a little more clearly. The ln of 8. Natural log of 8 is our solution here. So we could go plug that in, and we would see that we would get the right answer. But there's no danger of plugging anything weird in here. We can plug anything we want into an exponential function. It is the range that has some sort of restriction here. So there we go. All right, another example of doing what will turn out to be another quadratic substitution, because I've already done this problem, and that's the reason that it's here. But sometimes if you don't know what to do, you can just start doing stuff that you know is valid and see what you get. A lot of times these problems can just feel like puzzles, and they're puzzles to solve. So what I'm going to do here is take a look at this 36 to the x here, and I can rewrite that as 6 squared being raised to the x power. Next I have 6 times x, or 6 raised to the x plus 1. So what I can do there is use my properties of exponents to write this as 6 to the x times 6 to the 1. So remember that if you have two exponentials of the same base, you can just add those exponents together. That would give us x plus 1. I'm just using that property kind of in reverse. There's no direction to that property, but that is the property I'm using there. I can subtract 40 from both sides and set this equal to 0. And now, maybe if I write this a little bit differently, I could rewrite this as 6 to the x being squared. So I'm just using the commutative property of multiplication there to move those around, minus 6 times 6 to the x minus 40 equals 0. Now we have something that is in some quadratic form here. So I could make my substitution and say, okay, let's let u equal 6 to the x, and then I can come back and rewrite this as u squared minus 6u minus 40 equals 0. And now I think this looks like a much easier problem. Now, was that like the simplest or most straightforward, or like, oh yes, I totally know what to do to solve this problem, kind of first steps here? No, I don't think so, which is why we're doing this one now. So if you see something like this later, you'll have some intuition about what to do. So now I think that we can factor this left-hand side equal to 0. We'll have u, and I think that negative 10 and positive 4 will factor this for us. That will give me negative 6 in the middle and negative 40 at the end. Cool. So this tells me that u equals 10 or u equals negative 4. But again, we weren't trying to solve for u, we were trying to solve for x. So let's make that substitution back. We've got 6 to the x equals 10, or 6 to the x equals negative 4. Just like in the last problem, we're going to throw out the negative version because, again, the graph of 6 to the x looks something like that. It will never hit negative 4 down here. So this is an extraneous solution. We'll just write extra for short, and I can focus on this other side here. So focusing on 6 to the x equals 10, I will take the natural log of both sides. It doesn't really matter which log we take. I could take log base 6, but I'm not able to put that into a calculator if I wanted to get a decimal approximation, which we don't always want, but sometimes it can be helpful. So I'm taking the natural log of both sides here. Now I can use that power property to pop this x down in front, and I've got x times the ln of 6 equals the ln of 10. And now I can divide both sides by that natural log of 6. On the left-hand side, they cancel. That's the reason that we did that. And we get that x is equal to the natural log of 10 over the natural log of 6. We should just make sure that this, actually no, we know that this works because this is an exponential, so we are good here. I'm just trying to be hyper vigilant about checking our answers to make sure we're not plugging anything in weird here, but we're good since we started out with exponentials to start with. But here's our answer, and it's a very weird looking answer, but that is okay. This is what we get when we solve. This is just going to be some weird irrational number. If we plug it into a calculator, I don't know that I have that here, but we could figure it out. But this is a perfect solution. It is an exact solution, and that's often what we want for these problems anyhow. So there we go. All right, it looks like it is time to practice. So that wraps up this video for us. Please let me know if you have any questions. I'm always happy to help, and I will see you in our next video.